As mentioned, I am Bryn Lonsbrough. I'm going into a second year of my master's program at the University of Victoria, and I work with Dr. John Willis, an observational astronomer at UVic, to investigate the galaxy cluster XLSSC 122. Before we get into galaxies in the early universe and galaxy clusters themselves and how we observe them, I think it's best to sort of just briefly describe what is out there in space and what are the objects that we're talking about. So first up, we have stars. Now stars are things like the sun. You see them every day. And stars are really very dense objects that have quite a bit of energy within them. They're very bright and luminous, and it's what forms the most visible portion of the universe, even as they are found within other objects like galaxies and galaxy clusters. Galaxies, a step up in size by quite a bit, contain hundreds of billions of stars, a vast amount of stars, as well as gas, material that has not found its way to form stars just yet at various different temperatures. They also have dark matter, which is mass in space that we cannot see visibly. Stepping up in size even more, we get to galaxy clusters, which is the object of study that I'm most interested in. A galaxy cluster visually appears as a large concentration of galaxies in the sky, but is a much more complicated structure than we initially thought when we first called them galaxy clusters, and we'll get to that. But the first question I think we should ask and answer is, how big are these objects and how far away are they? Now we use a handy metric of the speed of light as a measure of the distance between objects and two objects, because in space light travels at a very constant speed. That speed is 300 million meters every second. Now that doesn't really mean anything to us in our lives. We don't see things moving that fast. Our eyes can't comprehend that speed. So before we get into how fast light is, let's ground ourselves. So something that I've taken to doing since I've moved here to Victoria about a year ago is I like to walk from my home in Esquimalt downtown near the legislature building. It's a nice building. I make the walk once a week or so. It's nice to see the lights lit up at night on the holidays. And yeah, so let's start our journey there for the purpose of measuring time and distance. Now, your average person walks faster than 1 meter every second, but we're going to slow things down and we're going to take a nice leisurely walk at 1 meter every second. Now that's a pretty consistent pace. If you travel for a long time period, you're going to get where you want to go on Earth. But how long would it take you to go around the Earth? Well, the Earth, it has a circumference of about 40 million meters. It's quite uniform across. It's very spherical. And that, if there was a road that were to go all the way around the Earth along its longest straight line point, and you were to walk for 24 hours a day, 7 days a week, no resting, no stopping to eat, it would take you 462 days to walk around the Earth. I think most people would consider that a pretty large amount of time to spend walking. Now, but let's do that 7.5 times. That seems like a bit of an odd number. Why did you choose 7.5 times? Well, because 7.5 times 40 million meters is 300 million meters. Now that would take 10 years. And if we go based on sort of historical accounts of how long 10 years is, we look at perhaps Homer's Odyssey, where it takes Odysseus 10 years to return home from Troy. So you could call 10 years, I think, fair to say, a bit of an epic journey of sorts. Let's just ignore the 7 years that he spent at one place on an island, but that distance, 300 million meters, if we remember, is the speed that light travels in a single second. So I think that starts to get close to a bit of how fast light's going, and if we're using it as a measure of distance, how big things are in space. Because for what is in our perspective, a 10-year-long epic journey, light travels in a single second. Given that speed, how far away is the sun? Well, the sun is about 150 million kilometers away, so it takes light roughly 8 minutes to get here from the sun. In our day-to-day lives, let's switch our perspective from light to our own perspective and kind of imagine that we're light and that we're traveling on Earth. But we're traveling at the speed of light, and Earth has been stretched to immense distances. It would take, so to get somewhere in 8 minutes, starting at the legislative building downtown, we could take, for example, the Bug Zoo, which is, past the Empress Hotel, downtown a little bit more. You go around the Inner Harbor. It's a quick walk, Things don't really happen, things don't really change much when you take 8 minutes out of your day. Another fun bit of information from this is, since it takes light 8 minutes to reach us from the sun, receiving all the information from the sun 8 minutes delayed. If the sun were to, right now, explode or change color, we wouldn't see it for 8 minutes. If the sun were to disappear even, we wouldn't really know it had for another 8 minutes. Okay, so that's a pretty reasonable time scale, 8 minutes, okay. Now the Milky Way is a little bigger. It's about 950 trillion kilometers across, which ends up being around 100,000 light years. And now, well, this entire story and comparison's kind of gone away. Because how many of you have taken a trip that lasted 100,000 years? Probably none of us. In fact, we have to go all the way back to our common ancestors, the original humans in Africa. About 100,000 years ago is when we as a species began to move out of the African continent. This is prehistoric times. And all those galaxies that you see in space, which in sometimes might take up like a small little portion of your little image that you get of space, that takes 100,000 years for light to cross those distances. The object that I study is the galaxy cluster, XLSC 122, which is 1 million light years across. It's far from the largest galaxy cluster that we know of today, but it's very far away. It's 10.4 billion years old, or 10.4 billion light years away from us, which is much closer to the start of the universe than it is to our present day. In fact, one of the largest clusters that we've seen is the Coma cluster, which is 20 million light years, 20 times that distance across. 20 million years ago was before humans walked the Earth, really. It was during the Miocene era, when there were megalodon, giant sharks that ate whales in the ocean. I'm very glad that we don't live in those times, because that would be terrifying. But if we consider, if we wrap this up a little bit and we consider light as something that conveys information from the past, then 8 minutes is not a long time. 100,000 years is a long time. The information being sent across these distances is so old. So old, in fact, that we can use it as a sort of time capsule for the early universe. The most distant object that I found that we've observed was with the James Webb Space Telescope, called GLASS C13, at about 13.5 billion years old. This is only 0.3 billion years after the Big Bang. Very close to the early universe. And, well, the image isn't great because it's very far away, but it's very impressive how far away we can see with our modern instruments that we would never be able to see with our own eyes. That leads me to the second question. Now that we know how far away these objects are and how large they are, the next question I think that is most useful to impart is, why are these three separate objects? What are they made of? And why don't they all fall into one big object? So I'm going to explain two pieces of information, or two properties, that each of these objects has, separately and inside of them. The first is mass. Now, I think we all have a rough conception of what mass is. You know, mass is what makes up your pen, or the moon, or the chairs that you sit on, or even your bodies. And something that mass does is it attracts everything else with mass. So, for example, the Earth and the moon are attracted to each other based on their mutual mass, which means that they will, over time, get closer and closer together. If you were to remove every other effect in the universe except gravity and except two pieces of mass, let's say two pieces of sand, and place them on either end of the universe, eventually they would fall together. Gravity acts over immense distance, but it does fall off pretty quickly. So something like the Earth, we can jump and we can return to it. I probably shouldn't jump with a mic pack. But we return because the Earth is very massive in comparison to us. Technically, we are also attracting the Earth upwards to us, but it is a very small amount because the Earth is very hard to move. So everything wants to reach one point. That brings us to the second quantity, energy. Things in space can be considered as particles. Now this is a bit of an approximation, an abstraction that astronomers like to use a lot, where they take a star and they say, oh, this is now one thing. We don't care about the interior of it, or this is a galaxy. We're just going to call it a speck. But it helps, it reproduces most of the effect that you're seeing. So when we think of particles, we think of gas, and gas has a temperature. You can feel, say, the air, and you can feel the temperature of the air. When it's hot out, the air is imparting energy onto our skin. When it's cold, we are transferring energy away from us into the air. That's a rough general interpretation. The higher temperature something is, the greater energy it has, the greater resistance it has to being moved. Which means, similar to when you have a hot air balloon, something that's hot resists being compressed down. So in a hot air balloon, you heat the air, it expands, it becomes less dense, it creates buoyancy. But all the while, it's becoming greater in volume because that increased temperature is causing more collisions with the exterior of the balloon, which counteracts the pressure from the atmosphere. And so this is what we call a bit of like an equilibrium state, whereas the force pushing inwards is equal to the force pushing out. And all three of these objects that I've mentioned are typically in a type of equilibrium similar to this. If we start with a star. Now a star is a large collection of mass that has gotten cold enough to contract down and to form a very compressed ball of material. And then what happens is a fusion reaction is ignited, and all of that material begins jostling together, creating heat, heating it up, increasing its temperature, increasing its energy, at which point it begins to radiate heat. However, at that point, it is too late. The mass is too close together to be thrown away. Gravity acts much more powerfully at closer distances. So all that material is trapped. However, material outside of it is then energized and can't fall in as well and is ejected away from the star. So this is a brief simulation showing kind of how that works. It slowly compacts together and then expands outwards, irradiating the surrounding gas. Now, when this happens over the span of hundreds, thousands, hundreds of billions of stars, you get a lot of regions in space that each have stars that are then heating up the gas around them. But that all composes one larger region of gas and stars that are all rotating and orbiting and are attracted to a singular point, and that are all buoyed and kept away by their own energy. They don't all collapse to form a single star because there is a consistent re-energizing of the material. So this is a simulation of a galaxy formation, and so this roughly occurs by the merging of a lot of different subgroups into one larger galaxy. And as you can see, the centers of these are dense, but they're not just one star. They do still maintain a structure, and as they rotate, you can see this really cool effect of sort of this change in rotational speed as you go to farther and farther distances, where the material out here is moving slower in terms of angles across the sky than that middle portion is, which is very quick, rotating very fast about its center. Until, eventually things settle down, like with our own Milky Way, where you get these very distinct patterns that appear, spiral arms, bulge-like structures in the center of galaxies, and these long trails on the outer edges. But there's a limit to that range, to where that structure is stable. And once we exceed that limit, we get to the scope of space of a galaxy cluster. So this is a simulation of dark matter in the universe on very large scales. And one of the fascinating things that we've observed and that we theorize about the universe is that at very large scales, the universe looks like a web or a interconnected structure of filaments. Filaments as in the pieces of metal, for example, that you find in a light bulb. And where we find that these filaments interact and collide and all form into one area, a node between filaments, you get what we observe as galaxy clusters, which is a large amount of mass that has accrued in one area. Now these galaxy clusters are composed of hundreds of galaxies. And you can see that they range in size and mass as you get farther and farther from the center of the cluster, until you get to the very middle, where you have this very bright, very large object. However, there's also this very diffuse, like cloudy material that surrounds them, which is actually something that we can observe. So how do we observe these galaxy clusters? Well, we have two primary methods of receiving information from these clusters. On the right is a picture of the galaxies themselves. These objects we see in images of the sky. We see spiral galaxies, we see helical galaxies, we see red, we see blue, we see a wide variety. They are perhaps by far the most interesting objects, or varied objects at least, to study in these clusters. But on the left, I have this blob, this like cloud of purple gas out in space. What is that? Well, that is what we call like an intracluster medium, or it's a plasma. It's a gas that has been superheated by falling into this deep gravitational well. And it doesn't compact or condense because it's gotten so energetic. It has such a high energy to it. As a fraction of the total makeup of these clusters, only 5% of a galaxy cluster is actually those very fun galaxies that we see. Another 3 times that, 15%, is in that plasma that I mentioned. The next 80% is in dark matter. So really the name galaxy cluster is a little bit of a misnaming, you could say. But it's not one that doesn't make any sense. Early astronomers looked at the sky. They can't see the dark matter, clearly. It doesn't emit light, it doesn't absorb light. We don't see it. And they didn't see the plasma, because the plasma is very high energy, and I'll tell you in a bit, it emits light that we can't see with our eyes. So all that we're left to see is a big overdensity, a big cloud of galaxies in the sky. But let's briefly get dark matter out of the way so we can talk about the other bits. So on those large scales, where we have these large filamentary structures, you have webs of dark matter. And the reason why we know this is there, even though we cannot see it, is because we can see its effect via gravity on other objects nearby. Think of it like, a good analogy would be if you had a bucket on the ground, and you know that bucket, you've lifted buckets like it before, it's empty, or so it seems. You go to pick up the bucket, and you find it is much heavier than expected. Then you must conclude, obviously, that it is filled with invisible lead that you cannot see and that doesn't interact with light. That's kind of what's going on here. We see galaxies and we see this gas and we see that it's very hot, it's very energized. These galaxies are moving very fast and they're orbiting this common point. Well, there must be something there. There must be some extent of material there that is attracting it. So that's how we sort of characterize and observe where this dark matter is, despite being unable to see it. The plasma itself, though, is one of the most directly affected pieces from that dark matter. Because it's such a large cloud of material, it covers a lot of the dark matter extent of the galaxy. And as it does so, it also reflects the slight variations across the dark matter halo of a cluster. And there are two effects that we can observe based on its energy. The first is its interaction with itself. These are a lot of charged particles at this point. They've gotten so hot that they've broken their bonds in their nuclei. There's electrons, these negatively charged particles floating around, and there's protons, which are in the middle of these neutrons that have been separated. And what happens when these two particles interact, going at very high speeds around each other, is they attract each other, sort of like magnets. And as they do, they get flung in one direction or another direction. And as that happens, they kick away very high energy photons or light. So these end up being in the range of X-rays, sort of like at the doctor's office when you have like an X-ray machine, X-ray imaging machine for your body. Now, has anybody here seen an X-ray when you've gotten an X-ray done? No? Well, but have you, if you were lying on the chair, did you see the light from the X-ray machine? Okay, that's good. I was alarmed for a second. I thought perhaps we had someone who had their eyes swapped out for X-ray imagers. Yes, but so you observed what early astronomers didn't, is that you can't see X-rays. So what we do is we use very specialized space telescopes to see them. Here is the Chandra Space Telescope and the XMM Newton Space Telescope, which is the one that I use data from. And these things are built very long in order to corral these X-rays into a single detection point. But X-rays are not the only thing that we observe when we observe galaxy clusters' plasma. The next is something it's a little bit trickier to get, but I think you all get it. It's what we call the Sunyaev-Zeldovich effect. Now, Sunyaev and Zeldovich were two astronomers, and the effect that they observe is a decrease in light coming from the clusters in certain wavelengths. So what's happening here is you have all these high energy particles, and as light from the very early universe, from the Big Bang, reaches the cluster, it is collided with by these particles, which give this light extra energy and boosts it, which seems counterintuitive because I just said we observe less light in this wavelength from these clusters. What's going on there? Well, as the photon is shifted upwards in energy, we've observed a very small, narrow band to try to capture the peak of this light. But since we've shifted the energy upwards, it's shifted that peak away from our filter of observation. So even though there is more energy in the light that's being sent to us, it's outside of the range of our detectors. And that's very nice because we can see this decrement and we can characterize this as being a galaxy cluster. Especially now that we've advanced a little bit beyond very large horns held up to our ears on the ground to very sophisticated space telescopes that create very detailed maps of this early cosmic microwave background noise. But now we have that out of the way, we get to the galaxies within the clusters. So the plasma that I mentioned before is very useful for determining the bulk properties of the cluster itself. It reflects the dark matter halo behind it, and it gives you a sense of the size, scale, the scope, and the mass of the cluster itself. The galaxies within them, though, are interesting in that we can use them to observe an accelerated behavior in galaxies. And what I mean there is that when we observe a galaxy cluster and we observe the galaxies within them, we see that they tend to be very red. Now, these are objects that I've highlighted because of their color, but their location within the cluster is determined through other techniques. However, what we're looking at here is these galaxies in these clusters are much redder and more compact than their neighbors. Now, not all of these galaxies are in the cluster. In fact, most of them are not. This is one broad image. But when you compare objects inside and outside of the cluster, and you look at their colors, you find that the ones within the cluster are much redder. You find that they have much more compact, circular or spherical shapes to them. Now, why is that? Well, as one prevailing theory is as these galaxies enter the cluster, all of the material that's in them is pressed together. And when materials press together, you begin to form more stars, which are initially bluer, but after a very long time of this accelerated use of the material within the galaxies, you've lost all that star-forming material. So by the time you reach the center of the galaxy, you're not forming many new stars. You're dead, as you can call these galaxies. The difference in shape can be explained by the stripping away of material by the plasma as you enter into it, or through other effects, through the merging of galaxies as they interact with each other in this much denser environment. Now, let's zoom in, before we end, on the center of the cluster. You see this bright galaxy here. This is what we call the brightest cluster galaxy. It's so named because it is the brightest galaxy within the cluster. And this closely coincides with the center of the cluster as seen through X-ray imaging. This here is an overlaid image of the XMM Newton data, the X-ray images I was talking about before, over top of the center of the cluster. And you see that that large galaxy is at a very similar location to this large cloud of gas. It lies well within its center. That's usually how we go about identifying and characterizing these clusters. There's a lot more that you can do with these, but when you see a cloud like that and a bright galaxy that's red, it's compact, it's spherical, you have a pretty high likelihood of that what you're observing is a galaxy cluster. But one thing that I think is perhaps more visually interesting for clusters that are not so far away that we lose all these features is the concept of a jellyfish galaxy. I'll leave you with this one before you leave. A jellyfish galaxy is named because it has all these bright blue tendrils behind it. Now, these are galaxies that are at the edges of clusters that are just beginning to enter. And this is where we start to test some of our theories. And these are still pretty hot topics of astronomy right now, where as these blue galaxies enter the cluster, all of that loose gas that's floating about the galaxies is ejected away because it enters into this dense environment. But the stars, which are much denser, push forward. And what that leaves behind these galaxies is these long trails of gas that then begins to cool on its own and collapse down and form stars, leaving bright blue trails behind these infalling galaxies. Just thought that was pretty neat. And yes, that's the end of my talk.